Thank you very much for being here. I'm very happy to be again at the Plone conference. My first conference was in, I think it was year 2005, the Vienna edition. It was the first one also for a turtle. Me, Stefano, and Massimo drove to Vienna, and then the one in Naples, Budapest, and then many years without the Plone conference. So I'm really happy of being here. And when they asked me to make this talk, so I will not rant, I promise. And I hope you will enjoy this talk. We will talk about some mathematics, then the Renaissance, and then talking about not having enough mathematics. So let's begin with some maths. Everything begins in ancient Babylonia. When they had floods, they had the problem of finding again where the fields were, and during doing measurement. And so in a sense, in ancient Babylonia and in Egypt too, they invented geometry. These two stones, the one on the right, I think, thanks to this very good venue, you can see that there is a shape, you see, something like some triangles. And in fact, on this stone, there is this picture, and both figures are taken from this paper that you find on the web. It's freely available. Just look for the Cuneiform Digital Library Journal. And it's fun because you see it's a field. If you read the sentences, that the field above was by a Louis Utu, the doctor. This reads that down there there is cattle, etc. There is a canal on the left, etc. So they had the issue of solving equation in order to do this kind of measurement. And as the paper explains, they had to solve a particular instance of equation that called the quadratic equation. I think that you know what I'm talking about, because I think that all of you have seen this equation. I think it's done in every high school. And you ask for the value of x that solve this particular term, where a is obviously different from 0. Otherwise, it's a much simpler linear equation. The curve that you get is called the parabola. Okay, and I think that all of you have seen this stuff probably some years ago. In fact, just in case you forgot, and I would like to make a poll, how many of you remember or think they can remember, given a piece of paper and a pencil, which are the values of the solution of the quadratic formula given A, B, and C? Please raise your hand. Okay, fine. Okay, good. And yeah, for everybody else, the formula is like that. We have two roots, x1, x2, and they're given by this very simple calculation, this very simple algorithm. But that was not done like that at the time, because at the time they didn't recognize negative numbers as numbers. Numbers has to be positive quantities. If you think that they use that to measure the length of fields, canals, etc., it makes sense. So what's a negative number? don't have minus 1 meter, you know. So, in fact, they thought that, in fact, there were 3 different equations. They wrote that essentially like that, dividing the terms by a, or putting a equal to 1. So you see that all the combination for B and C being negative amounts to have a different, something that they thought was really different. So in a sense, they had a much more complicated software of what should have been, because they had different representation for the same stuff. And I think that you agree that what I showed to you is in fact software algorithms to solve even very simple equations. We will get back to that later. Let's move fast forward some millennia and get to the year 1494, where an Italian mathematician called Luca Pacioli publishes a book that's called Summa de Arithmetica, etc. And at the time, Pacioli was probably one of the most known and famous mathematicians in the world. He did many things. In fact, he was also a designer. That's a picture that I took 2 years ago at Archiginnasio from his book Divina Proporzione. I think that some of you could recognize that letter Q, because it's also the name of a famous book that was printed 20 years ago. And, well, even great mathematician makes mistake, because at the time they knew the solution. Obviously, it was already known 3,000 and more years before for the quadratic equation. But in Pacioli's opinion, the cubic equation was not solvable. It was very hard to find a solution, and he thought that it would not exist. What's the cubic equation? Well, it's pretty straightforward. It's like the one before, but with one more term. Now we have also an incognita that is raised to the 3rd power, and we call the corresponding curve as, we call it a cubic function. That's a cubic function. It's an N-shaped curve. And as you see, this one has 3 real roots, which are the places where the curve intersects the x-axis. Since this is a Plone conference, I had to show some Python code, and that's the Python code taken from the Wikipedia page of the previous picture. That's the one that was used to plot the function. Enough Python for my presentation. At the time, during the time that I'm talking about, so 15th, 16th century, it was the equation was usually written in a simpler form. They did some change of variable, which simply amounts to shift the curve so that the place where it flexes is on the y-axis, and you get a simpler form with just the cubic, the linear, and the known term. Okay, so nothing fancy. Now we get where the real mystery and the plot thickens. Despite Pacioli's conjecture, few years later, on his deathbed, a guy called Scipione del Ferro told to his friend Antonio Maria del Fiore that he had indeed found a formula to solve that cubic equation. Who was Scipione dal Ferro or Scipione del Ferro? You find both the names. He was a teacher at the University of Bologna, and at the time it was defined to be a matematico eccellentissimo, an awesome mathematician, one of the greatest of the time. Notice something that I find really interesting, that because of his mathematical prowess, he was able to get an increase of his wage by sixfold over 15 years. I hope that many of you had this improvement. Okay, assuming that you didn't start working for €1 for each month, and that you had just a starting money to start, like let's say a junior programmer, well, 6 times that money in just 15 years is not a bad achievement, in my opinion. And how did it get that? Well, they say that he was really able, when they did, let's say, challenges among mathematicians, he was the one that won most of the time, because he had the skill, he had the formulas. In modern terms, we will say that he had the algorithm or the software to be better than the rest. In fact, it seems that he had devised this secret software to solve an equation like that. But nobody knew for sure. A little detour. Do we agree that finding the values of x, y, and x2 in that formula is, in fact, an instance of writing perhaps a very simple algorithm? Something like very stupid, okay, take 2 values, multiply them, and then by 4, etc., etc. Is there anybody that does not agree with this position, that this is not software? It is software with strange rules, because all of the difficulty is essentially in finding the specification. I mean, the hard part is being able to write that formula like that. If you write another specification, let's say that you say that the solution is minus b plus minus the square root of b, not raised to the second power, minus 4ac, your specification is wrong. It can give you right results in 2 cases, if b is equal to 1 or if b is equal to 0, but everything breaks down. Nothing works anymore. After you have that specification, building the algorithm is, well, obvious, not only for us 5 centuries after the time of Pacioli and Del Ferro, but once you know some basic mathematics, it's pretty straightforward. And by the way, also executing that software, that algorithm, is not the hard part. And if you train a little, you can do that on the top of your head and solve a quadratic equation in a few seconds. Well, not for probably very large numbers, but I think you get the point. So, back to 16th century, and let's come in other 3 characters. Gerolamo Cardano, Niccolò Tartaglia, and Lodovico Ferrari. Remember, Antonio Maria del Fiore, the guy that they say got from Del Ferro the news that when he was alive, he had made the discovery of how to solve the cubic equation, learned that this mathematician called Niccolò Tartaglia was able to solve a specific instance of the cubic equation. You see the one right there. It's not the general one, because the squared term has a coefficient 1. So it's let's say, a class of cubic equation. He didn't believe him, and he challenged Tartaglia to a disfida matematica that can be roughly translated as a kind of mathematical fight. Preparing for the battle, Tartaglia found the more general formula, and in fact, in 2 hours, he was able to solve all the challenges that Del Fiore posed to him, and on the other side, Del Fiore failed all of them. 4 years later, Tartaglia revealed his discovery to Cardano under an oath of secrecy. Why did he do that? I read that historians think that that was because Tartaglia, and Tartaglia was not his real name, it was a surname that he gave to himself. Tartagliare is stuttering, and he was hit as a boy by a sword during a battle that left his jaw in bad condition, and for all of his life he was not able to speak normally. Remember that at the time teaching was done like that, speaking in front of students. So Tartaglia probably wanted to get from Cardano some help in getting better jobs position in some Italian university. Cardano, in the following years, worked by himself and with his student Lodovico Ferrari to find a general solution on his own. 3 years later, they happened to be in Bologna, in the house of a relative of Del Ferro, and they found this letter written in Latin, and that letter showed that Del Ferro had indeed found a solution, but he decided to keep it for himself, well, to have an advantage in that kind of disfide that we have been talking about. Reading that Tartaglia was not probably the first discoverer of the formula, he decided that he was not bound to keep the secret anymore, and since Tartaglia did not publish it by himself, 2 years later, when he published his Ars Magna, he wrote in that book the solution of both the cubic equation and of the quartic equation that he devised with the help of Ferrari. Tartaglia next year wrote his Quesiti et Invenzioni Diverse, and then he wrote that the real discoverer of the cubic equation, of the solution of the cubic equation, was indeed him, and that in fact Cardano learned it from him, and that in a sense that he was a really bad person because he did not acknowledge that he was not the real inventor of the solution. This started a long dispute over the paternity of the discovery, and it was fought by Ferrari on behalf of his mentor Cardano and Tartaglia himself. They had 6 disfide in 2 years, and after the last, Tartaglia gave up. And just to remark the importance of this stuff, at least for these guys, when Tartaglia went back to Brescia from Milan after he lost the last disfida, he was a teacher in Brescia. A few months after that happening, he lost his job. So, being a really good mathematician could improve your income by 6-fold in 15 years, and losing a disfida could mean losing your job. So it's real life at stake, not just numbers and formulas. So, who is the real winners? Well, these disfide are very interesting because they are the letters, the papers where we can read the whole story. And in fact, there is this letter where Cardano says that when they were in Scipioni's Ferrei Soceri house, they found this script, and also Tartaglia, in another letter, wrote about the paternity of Dalferro. Questa particolarità non mi pare licita doverla disputare né manco negare. It means, yeah, I know that Dalferro was probably the one that discovered it the first time. I don't want to deny that, but remember that at the time Dalferro has been dead by 20 years, so his real, let's say, enemy was Cardano. He had no issues in recognizing that Dalferro discovered this stuff before him. So let's try to be ecumenic. Most of the time you find this formula as Cardano or Tartaglia Cardano, but let's call it with the name of all the guys involved in its discovery. And this formula is quite harder to remember, and by the way, you write it in that form because after a change of variable, the one that I was telling you before, so you essentially move the curve by that change of variable and then divide so that the first term is just x to the third power, and then on P and Q, you have that. If you know some mathematics, you will notice something strange in this formula because, well, you know from calculus, from no, not calculus, algebra, from the general theorem of algebra that a cubic root has 3 solutions if we count the complex numbers. So, in fact, there is 3 numbers, let's say U1, 2, 3, that at the third power do the value minus Q divided by 2, etc., etc. And also that there are 3 values, V1, 2, 3. So, how could it be that we have every combination of 3 numbers with other 3 numbers and we don't get 9 solutions? Because at the end it's a cubic equation, so it also must have just 3 solutions. How could it be that the formula is correct, but it seems that it's not? The trick that's really bad explained in high school is that you don't take any combination of, let's say, U, I, and Vj, but only the combination whose product has the value minus P divided by 3. And look, there are in fact 3 pairs for which this equation holds, so in fact you get 3 roots as the theorem say. But that's something that people at the time didn't understand very well. Take, for example, this instance of the equation. If you apply the formula, you get that, okay? Cubic root of 2 plus 11 and multiplied by the square of minus 1. At the time, minus 1 was literally garbage. It was something that had no meaning, exactly as the negative numbers for the Babylonians. What does it mean to have a number and you multiply it by itself and it gives minus 1? It can happen. If you multiply a number by itself, it is positive. So what? And at the same time, if you solve that equation by other means, you find that it has 3 perfectly fine real solutions for square of 3 minus 2, etc., etc. So again, how can it be? Is it the formula wrong or is it correct, but is there some trick that we don't know about? How can we get rid of these strange things? And by the way, okay, we have found the formula for the third and fourth order equation. Can we go on? What about the quintic? Or can we prove that there is no solution? This kind of question took more than 200 years, almost 300 years to get properly answered. In fact, the end of the research, let's say about algebraic equation, was done after the work of Lagrange and then Gauss by an Italian guy called Ruffini that wrote the first proof, but it's incomplete, and then by Abel that in 1824 and 26 wrote this paper where he proved that you can have a solution for algebraic equation till the quartic equation, but after the fifth degree, there's no way of trying to find a solution. Why did it take so long? In my opinion, and I think that we are moving from history to a topic that should be more of interest to our business, to what we do as software practitioner, is the fact that they lacked the abstractions needed to move forward. Babylonians didn't acknowledge that negative number existed at all. And Del Ferro and the other guys were comfortable with negative numbers, also with irrational numbers, like the root of 2, 3, etc. But they didn't know how to deal at all with that strange thing called the square root of -1, what we now call the imaginary numbers. Then people like Gauss and Abel, that knew complex number very well, were able to get the very first proof of the impossibility to find the general solution to an arbitrary algebraic equation, but it required the so-called Galois theory that was devised by Évariste Galois in 1830 to develop a more general theory. And now, let's say this issue is more or less settled. Let's get to nowadays. Let's talk about what happens when we don't have enough mathematics. Is there a field where, in my opinion, lacking of abstraction is hindering progress? Yes, I think it exists, and I think you already guessed my position. I think that's called software engineering. I feel that we are in software engineering, well, not probably at the time of the Babylonians, but not more or less at the time of Scipione del Ferro. Some question for you folks. How do we specify what a software should and should not do? How do we validate the behavior of what we write? And how do we describe and communicate our architecture? Let's say that you have a very new fancy architecture built on hundreds of microservices that you orchestrate to provide some very interesting and complex service for your customer. You have been working on that for many years. How do you tell to your fellow practitioners, so people that work as programmers, that, yeah, software practitioner, okay, that architecture? Which tools do you use to think about that? I think that there is only one answer. Oh, well, I know only one, but I'm open to suggestion. And the fact is that everything is done writing text, sentences, reports. You may have tables, diagrams, graphs. But even if that fancy microservice architecture is drawn with boxes and arrows and colors and fonts of many shapes to convey some information, that diagram, that graph is not done for some other software to be used in order to provide information to you. It's something that you, as a learned person who knows what's a microservice, what's an HTTP request, and the database, and the record is, etc., 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 will get from reading this description of the system. I am not saying that the theory of algebraic equation is the solution to this problem. What I want to stress in this talk is this, that the tale that I told you was just to focus on a particular moment in time of the history of mathematics, where I think that we see pretty well how moving forward is stuck until we are not able to go from one language to another. The story that I told you is the story of people that had to invent, to discover new symbols, a new way of understanding what they were doing. And as a matter of fact, I don't see this happening for software engineering. I'm not saying that I don't see new programming languages. There are too many of them. I don't see any new language to talk about programming languages, about the architecture of the software that you write with that or that other programming language. To do the stuff that I told you before, validation, specification, etc. What we did? Well, we did a lot, but I think that we focused too much on other issue. Let's take, for example, what happened with the agile movement. I think that pretty everybody in this room more or less knows what I'm talking about. I'm not going to read again the manifesto. It's a position by some people, skilled professional, very smart people. And what does it say? Yes, it says a lot of very, very fruitful and interesting things, but they do not deal with software development. They deal with something else, really important, involving the customer, communication, how we do build better contracts, how do we build an organization, how do we deal with the people that have to write the working software that we sell to other customers and that other people will use. And Agile achieved very important results. Don't get me wrong, I don't want to get back to developing in a pre-Agile time. That's not what I'm going to say. I'm saying, okay, we have not improved enough in the practice of how do we do the software thing, okay? How could we do that? There is this paper written by Eugen Wigner in 1959, 4 years before he won his physics prize. And the title of the talk of the paper, as you see, is The Unreasonable Effectiveness of Mathematics in the Natural Sciences. He starts the paper with this story. I don't know if it's a true story or a made-up story, about two friends that meet after a long time, and one of them is he works as a statistician, and he explains to his fellow friend what he does for a living. So he says that he's able to predict what happens in population, okay, how do they change over time, and the friend is skeptical and start asking questions. How do you do that? You know, this strange curve called the Gaussian, etc., etc. And at a certain point, the friend says, oh, and what that strange symbol that's on this paper? Well, it's pi. What's pi? Well, you know the Greek letter, the one that appears in the formula, for example, of the area of the circle, or when you measure the circumference of the circle. And the friends say, oh, you're pushing your joke too far. Surely population has nothing to do with the circumference of the circle. Well, problem is it has to do. And well, my position is that we don't have enough pie, but, okay, that's the slide with the picture for Irene. She's not here, but I think she will like the effort that I made in doing this slide with a picture. And you can picture your favorite random venture capitalist from Silicon Valley boasting, yes, who cares? We don't have pie and that stuff, but we built the internet. We changed the war. We created new market, disrupted old one, okay? The world is different. It has been changed a lot in these last 10, 20 years, and that's because of the software that we wrote because of our software. So we did big achievements. Yes, software built a different world, but my opinion, it should be a better world. Thank you. I don't know what you think about that, but think, for example, about safety. Not physical safety, but safety about your personal information, about digital rights, about your privacy. Do you really feel safe every time you use services, let's say you use stuff on the internet? I don't think so. And many of the tools that we helped writing are, was it me? Who knows? Could be building not just a police state, but a police world. Okay, the risk of increased surveillance because of software that was built with other intention in mind, the best intention, is real. We should try to build better software for the world. We need to be better at understanding the system that we contribute to build. We need to be better in guaranteeing that this system will be safe, that will not be misused. We need to have tools that allow us to do less mistakes. And last but not least, we need to be better in communicating the complexity of what we do, in communicating the impact of what we build, the implication in the real life of other citizens, not in the world of the solution of the cubic equation. Okay? I think we need a cast to find a better theory of software, because you know there is nothing more useful in practice than a good theory. That's not mine. It's by Kurt Lewin, but I think that theory may come only from the only unreasonably effective tool that we ever had, and that we also, as software practitioners, should try to move forward. I was amazingly happy in seeing some presentation yesterday where these teams rang a bell. I'm talking about the presentation by Zupan about typing in Python. I think about this slide by Eric yesterday, that Plone is dissolving, and then it's not the front end anymore or just the back end anymore. It is not the ZODB. So what's Plone? Oh, well, Plone is an API contract, the stuff that provides security, flexibility, etc. Okay, that's fine, but why are we describing that just in English? Plone should be an equation, the equation that solves the formula of the best CMS, and the software that you write is the proof that the formula is indeed true. That's what I hope someday we will achieve. Ladies and gentlemen, thank you for attention, and thank you.